Welcome to Cosmic Sedation, where you can drift away in comfort. Tonight's journey takes us to They Reached the Edge of Space, something pushed back, a story that promises to be both mysterious and serene. Don't forget to subscribe and like if you're enjoying the ride. Where are you tuning in from tonight, and what time do you usually fall asleep? Let's hear from you in the comments below. As we begin this peaceful voyage, allow yourself to settle in. At 80 kilometers above sea level, where skies should grow dark, particles multiply in a frenzy of light. This is not merely darkness. It's a zone where cosmic rays collide with Earth's upper atmosphere, creating an invisible cascade of subatomic particles, a particle shower, illuminating the vacuum with brief bursts of energy. Each collision shatters atomic nuclei into fragments that spread like ripples on a pond. These fragments move faster than sound could ever travel, their paths bending slightly as they interact with the thin air here. The temperature plummets to minus 230 degrees Celsius, yet this cold is not just an absence of heat. It is a condition so extreme that water would instantly sublimate into vapor without passing through a liquid state. At sea level, similar cosmic rays pass through us unnoticed, but up here, their impact is magnified by the thin atmosphere, 28 times more intense than at ground level. For astronauts venturing close to this boundary, each collision with these high-energy particles could potentially alter atomic structures within their spacecraft. The Kármán line, marking the official edge of space at 100 kilometers altitude, is a conceptual threshold rather than a tangible one. As craft ascend towards it, they experience a brief period of intense vibration as they transition through Earth's thermosphere, a region where air density drops to about 1/1,000,000th that at sea level. This thinning atmosphere means conventional aircraft cannot generate lift here, requiring rockets instead to push against the diminishing medium. Yet, despite this near vacuum, particles continue their relentless dance, each collision leaving a fleeting mark in the fabric of space-time. For those who venture beyond Earth's protective shield, the effects are profound and immediate. At 80 kilometers altitude, human bodies would face rapid decompression, with blood boiling due to the lack of pressure, were it not for specially designed suits or pressurized cabins. The particles here, while invisible to the naked eye, bombard every surface they encounter at velocities approaching the speed of light. These energetic interactions are a reminder that even in what appears as empty space, there is constant activity, energy and matter intermingling in complex choreographies. If we could perceive these particle showers directly, it might seem like a storm of fleeting sparks lighting up the void. As spacecraft breach the Kármán line, they encounter not just the absence of air, but also a layer where Earth's magnetic field exerts its final influence on incoming cosmic rays. This boundary acts as a filter, altering the paths of these high-energy particles before they reach lower altitudes and greater densities within the atmosphere. The intensity of this particle cascade decreases gradually as one moves further from the Kármán line, but remains significantly higher than at sea level for many kilometers above it. For context, imagine standing on Earth's surface where cosmic rays pass through us harmlessly. Now consider that each second thousands more high-energy collisions occur just beyond our reach in space. Remarkably, this particle cascade is not unique to Earth. Similar processes happen around other planets with magnetic fields, such as Jupiter and Saturn. The energy dynamics at the edge of Earth's atmosphere are a microcosm of broader cosmic phenomena, where stars forge elements that eventually make their way into our bodies, and where particles dance in the vacuum between worlds. In this sense, the particle showers above us are both intimately connected to life on Earth and part of an ancient, universal process shaping all matter across the cosmos. At an altitude of just over 100 kilometers above Earth's surface, sound waves, those familiar vibrations that travel through air and water on our planet, begin to falter. As spacecraft breach this boundary, they experience a sudden push, not from any wind or fluid resistance, but rather from the abrupt cessation of aerodynamic forces. At degrees Celsius and atmospheric pressure less than 1/1,000,000th of sea level, the thermosphere becomes an expanse where sound ceases to exist due to a lack of molecules capable of carrying its vibrations. This zone, known as the Kármán line, marks not only the edge of space, but also the end of our familiar acoustic world. Imagine if you could hear the universe beyond Earth's atmosphere, what would it be like? Sound waves require particles to propagate, and at this altitude, they are all but absent. The pressure here is so low that even a whisper becomes impossible. For spacecraft ascending through this region, the silence is profound not in the traditional sense, but as an absence of any detectable acoustic signal. On Earth, we take sound for granted. It's how our bodies communicate with the world. Yet at this boundary between atmosphere and vacuum, the very essence of what it means to hear undergoes a radical transformation. The thermosphere thus serves not only as a physical threshold, but also as an auditory one. As spacecraft cross into space, they encounter cosmic rays that bombard them with increasing intensity, about 2.8 times more than at sea level. These high-energy particles are remnants of distant supernovae and black holes, traveling across the cosmos to reach Earth. Yet within this celestial deluge lies a paradox. While space itself is silent, it thrums with invisible radiation. The thermosphere acts as a buffer zone where these cosmic signals transition from detectable frequencies to electromagnetic waves beyond our hearing range. This environment underscores an ancient truth. Much of what we perceive is filtered through our biology, a limitation that space forces us to confront. The thermosphere, ranging from 80 to 600 kilometers above Earth, experiences temperatures as low as -230 degrees Celsius near the outer reaches. At such extremes, water cannot exist in its liquid form. It either freezes solid or sublimates into vapor directly. This region is a graveyard for conventional aircraft, which rely on aerodynamic forces generated by air flowing over their surfaces to stay aloft. Without this dense atmosphere, even the most advanced planes would plummet back towards Earth. Yet within this hostile environment, spacecraft find a different kind of challenge: intense vibrations as they transition into space. These jolts are not caused by atmospheric turbulence, but by the sudden shift from aerodynamic lift to gravitational freefall. It's a moment where technology must adapt to an entirely new set of physical laws. For a human body, crossing this boundary is no mere journey. It's a survival test. At degrees Celsius and pressures below 1/1,000,000th of sea level, the human body cannot endure without protective suits designed to maintain internal pressure and temperature. The thermosphere's vacuum would cause rapid decompression sickness, bubbles forming in the bloodstream that would be fatal within seconds if exposed directly. Yet this environment also harbors a paradox. While it is inhospitable for life as we know it, its cold temperatures slow down molecular motion, making time itself seem to stretch. If you could somehow observe from here, you might perceive the passage of minutes as hours due to the extreme conditions affecting the speed of atomic processes. In the thermosphere, sound waves vanish not just because there are no molecules to carry them, but also because they become part of a larger cosmic narrative, one that transcends our earthly experiences. The silence here is not merely an absence of noise. It's a testament to the vastness of space and the limitations of human perception. As spacecraft traverse this boundary, they leave behind the familiar soundscape of Earth's atmosphere and enter a realm where electromagnetic radiation reigns supreme. This transition underscores a fundamental truth. Our understanding of the universe is shaped by the tools we use to observe it. At an altitude of roughly 100 kilometers above Earth's surface, a spacecraft experiences a dramatic shift in its environment. Here, the atmosphere is so thin that it can barely be considered air, just 3/10,000ths of a standard atmosphere. This region marks the threshold where our planet's influence over space begins to diminish. Once beyond this boundary, known as the Kármán line, astronauts report feeling a sudden jolt or pressure, a sensation attributed not just to altitude, but also to the way Earth's magnetic field interacts with incoming solar winds and cosmic radiation. The magnetosphere, extending far beyond this point, acts as a protective bubble around Earth, deflecting charged particles that could otherwise strip away our atmosphere over time. Inside this shield, charged particles from the Sun are bent into paths by Earth's magnetic lines, shaping the space around us like an unseen conductor guiding traffic. These lines of force extend outwards, creating ripples that affect spacecraft trajectories and satellite operations in response to solar activity. During intense solar storms, the magnetosphere can expand or contract dramatically, influencing how particles interact with our planet. This variability means that satellites and spacecraft must constantly adjust their courses to avoid collisions with these invisible forces. Temperatures at this altitude plummet to a staggering -85 degrees Celsius due to the lack of atmospheric insulation. Yet, despite these frigid conditions, life thrives beneath this barrier on Earth's surface. The magnetosphere not only protects, but also channels some particles into spectacular displays near the poles, the auroras. These high-energy particles, remnants of supernova explosions scattered across the cosmos, are funneled by magnetic lines to create dazzling light shows at our planet's edges. As spacecraft navigate this boundary, they encounter a region where cosmic rays bombard them more frequently than at sea level by nearly 3 times. These high-energy particles can cause significant damage if not properly shielded, posing a constant threat to both equipment and crew health. The craft must endure these impacts with specialized shielding to protect against radiation damage. This ongoing challenge underscores how fragile our position in space truly is. Every spacecraft venturing beyond Earth's protective envelope faces an ongoing battle against unseen assailants. Within this dynamic system, the magnetosphere not only deflects harmful particles, but also channels some into spectacular displays near the poles, the auroras. These light shows are a visible manifestation of the energy exchange between our planet's magnetic field and incoming solar radiation. The same forces that protect us can create these dazzling phenomena, reminding us of the complex interplay between Earth and space. This dynamic interaction continues to be studied by scientists seeking to understand how we might better harness or predict its effects, offering both challenges and opportunities for exploration. Spacecraft must travel at least 28,000 kilometers per hour to overcome Earth's gravitational pull and reach space. This speed is necessary not only to escape gravity, but also to maintain orbit once outside our atmosphere. The acceleration required for this feat can be felt as a significant push or jolt by astronauts, marking the transition from suborbital flight into true space travel. At 100 kilometers above sea level, the atmospheric pressure drops to about 3.2 times 10 to the negative 4 pascals. This extreme vacuum presents an environment where water cannot exist in liquid form due to both temperature and atmospheric conditions. Human survival in this environment requires a pressurized suit capable of maintaining internal air pressure and oxygen levels for breathing, illustrating just how much life depends on Earth's protective envelope. The density of air at this altitude is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. Conventional aircraft cannot fly here because they require an atmosphere to generate lift through aerodynamic forces. Yet, even with these challenges, spacecraft designed specifically for space travel must overcome the intense vibration and shaking experienced as they pass through the thermosphere, a region around 8,600 kilometers above Earth's surface. The magnetosphere's deflection of solar winds is not only crucial for protecting Earth, but also influences space, whether far beyond our planet. These interactions create conditions that can affect satellite operations and even radio communications across distances up to 150,000 kilometers. Understanding this process helps scientists predict disruptions in technology-dependent systems, highlighting the intricate balance maintained by this invisible shield around our world. At an altitude of roughly 80 kilometers above Earth's surface, the atmosphere begins to thin dramatically. Here, the air is so sparse that each molecule of nitrogen and oxygen moves with greater independence, colliding less frequently than at sea level. As a spacecraft ascends beyond this point, it encounters conditions where temperatures paradoxically rise before plummeting, a phenomenon unique to the mesosphere's upper reaches. The mesosphere extends from 80 to 90 kilometers in altitude, yet its temperature climbs as high as -30 degrees Celsius. This unusual heat comes not from solar radiation, but from the collision of meteors with air molecules. Each meteor incinerates upon entry, releasing energy that briefly warms the surrounding gases, an intricate dance of friction and decay. Strangely, this warmth is fleeting. Beyond 90 kilometers, temperatures drop sharply into the thermosphere, where they can plummet to -85 degrees Celsius. The mesosphere's temporary heat serves as a stark reminder of how transient conditions in space truly are. At the boundary between the mesosphere and thermosphere, around 100 kilometers above Earth, the Kármán line marks the transition from where aerodynamic forces predominate to where orbit becomes necessary for spacecraft stability. Here, cosmic rays increase by nearly threefold compared to sea level on Earth. These high-energy particles, born in supernovae or solar flares, bombard the upper atmosphere with relentless intensity, adding an invisible layer of radiation above our heads. Yet despite this energetic assault, life down below remains sheltered by Earth's protective blanket, a testament to the planet's ability to shield its inhabitants from cosmic threats. Interestingly, at this altitude, the density of air molecules is so low that they are spaced approximately 10 kilometers apart on average, making collisions between them exceedingly rare. As spacecraft breach the thermosphere, they encounter a realm where air density drops to less than 1/1,000,000th that at sea level. This extreme thinness challenges conventional notions of atmosphere, transforming it into an environment so sparse that sound cannot propagate, and lift is all but impossible for aircraft without rocket propulsion. In this vacuum, each molecule's movement becomes a solitary event, separated by vast distances. The thermosphere's chilling temperatures are not just cold, they are cold enough to turn water vapor directly into ice crystals, bypassing the liquid state entirely, a process known as sublimation. This environment underscores how quickly and drastically conditions can change in space. Astronauts often report a sensation of being pushed or jolted when transitioning from suborbital flight into space. This push is not due to any physical force, but rather the sudden cessation of aerodynamic drag. As the spacecraft leaves the mesosphere's last vestiges, it enters an area where there are simply too few air molecules to exert meaningful resistance. The change in pressure and temperature marks a critical threshold. Beyond this point lies the realm of orbit, where sustained motion requires more than aerodynamics. It demands velocity sufficient to overcome Earth's gravitational pull at over 28,000 kilometers per hour. While conditions in the mesosphere and thermosphere are extreme by human standards, they are but a fraction of what awaits deeper into space. At the edge of these atmospheric layers, cosmic rays bombard spacecraft with increased frequency, adding to the challenges faced by those who venture beyond Earth's protective envelope. The journey through this boundary region is brief yet profound, marking a shift from an environment shaped by Earth's gravity and atmosphere to one dominated by the vastness of space itself. Here, where temperature paradoxically rises before plummeting, lies a fragile frontier between our planet and the cosmic void that surrounds it. The astronaut's body is suddenly gripped by a profound shift as they pass the Kármán line, where Earth's atmosphere thins to near vacuum. This boundary marks the edge of space at approximately 100 kilometers above sea level, an altitude where gravity's pull is still significant, but no longer strong enough to support aerodynamic flight. As their spacecraft surges past this point, a noticeable push is felt, not from any external force, but rather the absence of air resistance. This sensation is akin to floating in water when suddenly entering deep, open waters. The human body begins to adapt to microgravity almost instantaneously. Blood that once pooled in the lower limbs due to Earth's gravity now redistributes evenly throughout the body. The astronaut's heart adjusts its rhythm, pumping less frequently and with reduced force as it no longer needs to counteract the pull of gravity. This fluid shift can cause temporary changes in vision clarity for some astronauts, a phenomenon known as space adaptation syndrome. Remarkably, this process mirrors the physiological adjustments made by deep-sea divers who transition from surface pressure to the crushing depths below. At this altitude, the temperature hovers around degrees Celsius. The absence of atmospheric molecules means there is no medium for heat transfer or insulation, leaving objects exposed to the cold vastness of space. To maintain body temperature, an astronaut's suit must provide artificial warmth, much like a winter jacket, but far more sophisticated. This environment highlights the stark contrast between Earth's regulated climate and the extreme conditions just beyond our planet's envelope, reminding us that life on Earth is cocooned in a relatively narrow band of habitability. As they ascend further into microgravity, astronauts experience a peculiar sensation. Their body fluids float freely within them. Bubbles form inside veins, similar to what happens when you open a bottle of soda too quickly. These bubbles are not dangerous, but do highlight the extraordinary conditions of space travel. The human body, designed for Earth's gravity, now finds itself in an environment where even internal processes behave differently. This fluid shift can lead to a temporary loss of bone density and muscle mass, as muscles that once worked against gravity no longer need to perform their usual functions. The sudden transition from suborbital flight into space triggers a brief period of intense vibration within the spacecraft. These vibrations are caused by the rapid changes in atmospheric drag as the craft breaks free of Earth's gravitational field. This shaking can be unsettling for astronauts, who must rely on training and equipment to manage these forces. The Kármán line marks not just an altitude, but also a shift from aerodynamic flight to orbital mechanics. It's a boundary where machines are tested to their limits, and human endurance is pushed in ways that are both extraordinary and humbling. At this edge of space, cosmic rays bombard the spacecraft at rates nearly 3 times higher than they do on Earth's surface. These high-energy particles originate from distant parts of our galaxy and beyond, traveling at velocities close to the speed of light. The increase in radiation exposure here is a constant reminder of how delicate life forms are compared to the vastness of the universe. For astronauts, this environment represents both an incredible opportunity to explore beyond Earth's bounds and a challenge to adapt their bodies and minds to conditions vastly different from those on our home planet. At an altitude of roughly 100 kilometers above Earth's surface, a curious phenomenon occurs as atmospheric pressure drops to about 3/10,000ths of what we experience at sea level. The molecules of air are so sparse that they no longer cling together in familiar ways, each floating almost independently through the vacuum. This thinning atmosphere is akin to walking up a mountain where oxygen becomes increasingly scarce. But here, it reaches an extreme. A human body would struggle to extract enough oxygen for cellular respiration, leading to hypoxia within minutes. At this altitude, cosmic rays bombard every object with unprecedented intensity. These high-energy particles from outer space strike atoms and molecules, creating showers of secondary particles and radiation. Strangely, the vacuum itself is not entirely empty. It contains a faint glow known as airglow, produced by excited oxygen and nitrogen atoms releasing energy in the form of light. This glow, though too dim for most eyes to see without instruments, serves as a reminder that even in near-vacuum conditions, interactions continue, just on an invisible scale. The sensation astronauts describe when entering space is akin to stepping out of a fast-moving car. There's no wind resistance, just the abrupt cessation of aerodynamic forces. The human body, evolved for Earth's thick atmosphere, encounters a stark contrast as it transitions from suborbital flight into true space. This moment marks a threshold where conventional aircraft could not hope to fly without rocket propulsion. In this environment, the air is so thin that each breath becomes an act of defiance against the vacuum's relentless pull. At this altitude, temperatures can plummet to nearly -85 degrees Celsius, far colder than any naturally occurring temperature on Earth's surface. The lack of atmospheric insulation means that objects exposed here lose heat rapidly through radiation. This cooling process is so efficient that even the warmest spacecraft surfaces cool down in minutes after re-entering from orbit. In contrast, the coldest laboratory on Earth can control temperatures to within a few thousandths of a degree Celsius. Nature's extremes are less precise, but far more dramatic. For example, an astronaut's exposed skin would freeze solid in just seconds if not protected by a spacesuit. As astronauts ascend into this realm of diminishing air density, their bodies undergo subtle shifts. The heart must pump harder to push blood through veins and arteries that experience reduced pressure due to the thin atmosphere. This increased workload can lead to physiological changes such as elevated pulse rates and heightened alertness due to less oxygen reaching the brain. In stark contrast, astronauts often report a sense of tranquility once they adapt to this environment, perhaps an unexpected psychological shift in response to the surreal conditions. The journey from Earth's surface to the edge of space is not merely a physical transition, but also a profound one for human physiology and perception. At around 80 kilometers above sea level, where the atmosphere thins dramatically, each breath becomes a reminder of Earth's embrace, a tenuous connection to our planet that we take for granted until it fades away into the vastness beyond. Here, in this liminal space, the boundaries between worlds blur as the familiar rules of terrestrial life give way to the alien conditions of near vacuum and microgravity. At the boundary of space, roughly 100 kilometers above Earth's surface, cosmic rays bombard the upper thermosphere with immense energy. These high-speed particles, primarily protons and atomic nuclei, originate from distant corners of the universe, traveling at velocities close to the speed of light. As they collide with atoms in the thinning atmosphere, each impact sets off a cascade of secondary particle showers. Remarkably, these collisions generate temperatures momentarily hotter than those on the Sun's surface due to their immense energy. Yet, because the density of air molecules is so sparse here, about 1/1,000,000th that at sea level, the heat quickly dissipates into the vast emptiness beyond Earth's atmosphere. This region marks the highest point where detectable particle showers occur on our planet. At sea level, Earth's magnetic field and atmospheric shielding largely deflect cosmic rays, protecting us from their full impact. However, as spacecraft ascend to this boundary, they encounter an environment devoid of such protections. Here, the sudden increase in cosmic ray collisions creates a micro-explosive effect, generating particle showers that decay into less energetic forms within fractions of a second. The particles generated during these collisions include gamma rays and neutrinos, entities so elusive they can pass through entire planets without interaction. Neutrinos have a mass so minuscule that trillions pass through your body every moment, unseen and unnoticed. This constant bombardment underscores the intimate connection between Earth's atmosphere and distant cosmic phenomena, reminding us of our place within the broader universe. As spacecraft breach this boundary, they experience brief periods of intense vibration, known as dynamic pressure or buffeting. These vibrations are not just due to aerodynamic forces, but also because of the rapid increase in cosmic ray collisions. The sudden influx of high-energy particles can cause minute electrical disturbances within sensitive equipment aboard the craft. Astronauts may feel these subtle pushes more than they see them, a gentle reminder of an invisible force at work beyond the edge of our atmosphere. Each collision at this threshold represents a fleeting yet significant event in the cosmic cycle. The cosmic rays that bombard Earth originate from distant sources, supernova remnants, active galactic nuclei, and other violent astrophysical events. These collisions are part of a grander process within our solar system, where stars explode with forces capable of reshaping entire galaxies. In this thin layer of atmosphere, the universe's energy flows freely, connecting the vast reaches of space to Earth's upper thermosphere in an eternal dance of subatomic particles. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. The spacecraft experiences a brief period of intense vibration and shaking as it passes through the thermosphere, which occurs around 8,600 kilometers above Earth's surface. This turbulence is not caused by wind or fluid resistance, but rather by the sudden change in atmospheric drag. The density of air at this altitude is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. Conventional aircraft cannot fly here because they require an atmosphere to generate lift through aerodynamic forces. The extreme vacuum conditions would cause rapid decompression sickness if a human were exposed without a pressurized suit. Spacecraft must travel at least 28,000 kilometers per hour to overcome Earth's gravitational pull and reach space. This speed is necessary not only for escaping gravity, but also for maintaining the trajectory needed to avoid falling back into the denser layers of the atmosphere below. The Kármán line, considered the boundary of space, is named after Theodor von Kármán in 1957. At an altitude of approximately 100 kilometers, the atmospheric pressure drops to about 3/10,000ths of a standard atmosphere. This thin layer marks the transition from Earth's atmosphere to the vacuum of space. The temperature at this edge can plummet to as low as degrees Celsius due to the lack of atmospheric insulation. These collisions also trigger the production of muons, unstable particles that decay into electrons and neutrinos within microseconds. Muons are particularly interesting because they can penetrate deep into Earth's surface, providing a window into subatomic interactions at the edge of space. This process highlights how cosmic events far beyond our planet influence even the most basic elements on Earth. The extreme cold ensures that any moisture would instantly freeze or sublimate into vapor. Water cannot exist in liquid form here because the temperature is too low and there's insufficient atmospheric pressure to maintain it. The sudden drop in air density also means that sound waves cannot travel, making this region completely silent from an acoustic perspective. The Kármán line, considered the boundary of space, is named after Theodor von Kármán in 1957. This altitude marks the point where Earth's atmosphere thins to near vacuum, and spacecraft experience a significant push as they transition from suborbital flight into space. The sudden change in atmospheric drag causes this jolt, which astronauts have reported feeling during their ascent, specifically a noticeable increase in G-forces lasting about 15 seconds. A spacecraft beyond the realm where aerodynamic forces cease to hold significance, at an altitude of approximately 100 kilometers above Earth's surface, a spacecraft encounters a layer that transforms communication. This is the ionosphere, extending from about 80 to 600 kilometers, where radio waves are reflected and refracted back toward Earth's surface. Here, signals can travel vast distances without significant attenuation, enabling global communication systems. Imagine sending a message across continents, whereas shorter wavelengths would be absorbed or scattered by denser atmospheres closer to ground level. Longer wavelengths navigate through these thin layers of ionized gases with ease. The ionosphere's role is pivotal in facilitating not just radio signals, but also GPS and satellite communications that we rely on daily. Despite its seemingly negligible mass compared to the rest of the atmosphere, this layer holds immense importance for human communication. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level, yet the ionosphere remains robust in its function. These high-energy particles strip electrons from atmospheric gases, creating charged ions and free electrons that are crucial for reflecting radio waves. The process is akin to an invisible dance of energy transfer, where light and matter interact in a delicate equilibrium. It's remarkable how this thin layer, though extreme in temperature, plummeting as low as -85 degrees Celsius, manages to sustain vital communication links. As spacecraft cross into space, they experience a significant jolt due to the abrupt change from aerodynamic forces to near-vacuum conditions. This sudden push is not just physical, but also symbolic, marking the threshold where human technologies extend beyond Earth's atmosphere. The ionosphere facilitates this leap by ensuring that signals can travel long distances without significant loss. It acts as both a shield and a messenger, protecting us from harmful radiation while enabling global communication. The ionosphere's influence extends not only into the present, but also into the future of space exploration and technology development. As we venture further into deep space, understanding this layer remains crucial for maintaining contact with Earth. Its reflective properties will be essential for communication systems aboard spacecraft exploring beyond our planet's immediate vicinity. In essence, the ionosphere stands as a bridge between distant points on Earth and humanity's expanding presence in the cosmos. This thin layer of charged particles is not just vital for present-day communications, it also holds clues about past solar activity. By studying variations in the ionosphere's behavior over time, scientists can infer historical patterns of solar radiation. This knowledge helps predict future space weather events that could disrupt satellite operations and communication systems. Thus, while the ionosphere facilitates instantaneous connections on Earth, it also provides insights into the dynamic relationship between our planet and its star, Sun. The density of air at this altitude is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. Yet, despite these challenging conditions, the ionosphere plays a crucial role in long-distance radio transmissions by reflecting signals back to Earth. This reflection allows communication across vast distances, linking remote regions and enabling global connectivity. The layer's ability to bounce signals is due to its unique composition of charged particles, which interact with electromagnetic waves in ways that are not possible at lower altitudes. At the edge of space, the ionosphere also acts as a natural barrier against harmful cosmic radiation. While it does not completely shield Earth from these high-energy particles, it significantly reduces their impact on life and technology near the surface. This protective role highlights the dual nature of the ionosphere. It both enables communication and safeguards our planet from potential threats. The layer's effectiveness in reflecting radio waves, while also filtering out harmful radiation, underscores its critical importance for both technological advancement and planetary protection. The Kármán line at approximately 100 kilometers above Earth's surface marks a boundary where conventional aircraft can no longer sustain flight without rocket propulsion. Here, The air pressure is roughly 30 to 10 thousandths of a pascal, an environment far more extreme than the negative pressure inside an aerosol can. While an aerosol can expel its contents against external atmospheric pressure, spacecraft at this altitude must maintain internal pressure to prevent instant decompression. This boundary highlights how technology adapts to extremes in both high and low pressure scenarios. At sea level, an aerosol can operate under a carefully balanced pressure differential designed to counteract the ambient atmosphere pressing inward. In contrast, space's near vacuum demands that spacecraft maintain internal pressure to ensure conditions similar to Earth's surface. Inside such vessels, air pressure remains stable at around 1 standard atmosphere. This stark difference underscores how our planet provides a narrow band of habitability, a fragile oasis in an otherwise hostile cosmos. As astronauts pass through the thermosphere around this altitude, they experience intense vibrations and shaking as their spacecraft battles against atmospheric drag. This phenomenon is akin to the slight rumble felt when opening an aerosol can, but on an entirely different scale. Each vibration is a testament to the incredible technological achievements required for exploration beyond Earth's atmosphere. The forces at play here represent critical junctures in human spaceflight history, highlighting the challenges faced by those who venture into space. The density of air at this height is 1/1,000,000th that found at sea level, making it nearly impossible for traditional aircraft to maintain lift. This near-vacuum environment forces spacecraft to rely on rocket propulsion and sophisticated life support systems to survive. In comparison, the aerosol can operate within a much more forgiving range of pressures and temperatures. The stark difference in these conditions serves as a powerful illustration of the challenges faced by those who venture into space. Conditions so extreme that even everyday objects like aerosols seem almost luxurious. The cold temperatures enveloping spacecraft as they cross the Kármán line can plummet to an average of -85 degrees Celsius, far harsher than any found inside an aerosol can. In this environment, water cannot exist in its liquid state due to extreme conditions. Surprisingly, some materials used in spacecraft insulation can actually contract and become brittle at such low temperatures, posing additional engineering challenges for designers. This is a stark reminder of space's relentless demands on human engineering. Systems must be designed not only to function, but also to survive and thrive under such inhospitable conditions. Despite the harsh conditions at the edge of space, this region is teeming with cosmic activity. Cosmic rays bombard this area at an intensity 2.8 times greater than what is experienced at sea level. This radiation serves as a constant reminder of the dynamic nature of space and its profound influence on Earth-bound systems. The contrast between the relative stability inside an aerosol can and the relentless barrage of high-energy particles in space underscores just how carefully crafted our technological solutions must be to withstand such environments, ensuring that humans can continue exploring these far reaches. At an altitude of approximately 100 kilometers above Earth's surface, a spacecraft finds itself at the edge of space, where atmospheric pressure drops to roughly 3/10,000ths of a pascal. This environment is so sparse that each molecule floats almost independently, barely interacting with its neighbors. Here, instruments aboard the spacecraft must be finely tuned to detect phenomena far more subtle than the violent collisions of cosmic rays or solar winds. Among these instruments are those designed to sense the presence of dark matter, an elusive substance thought to make up a significant portion of the universe's mass. The detectors are calibrated to pick up signals from weakly interacting massive particles as they pass through. These particles traverse space like ghosts, undisturbed by electromagnetic forces that give rise to the familiar world around us. On Earth's surface, such signals would be drowned out by background noise, but at the edge of space, the environment is more conducive for their detection due to its extreme vacuum. This boundary, where Earth's magnetic field begins to weaken and cosmic rays bombard with increasing intensity, offers unique conditions for probing the universe's most mysterious components. Instruments here can operate with greater precision, thanks to reduced interference from atmospheric particles. As the spacecraft crosses this threshold, it experiences a brief period of intense vibration due to the transition from aerodynamic flight to free fall. This jolt marks the point where Earth's grip on objects begins to weaken. At such heights, Earth's magnetic field forms an intricate web known as the Magnetosphere, extending far into space. Within this region, charged particles are trapped and guided by magnetic fields, creating a dynamic environment ideal for dark matter detection. The magnetotail, a long extension of Earth's magnetic field behind us, acts like a giant particle funnel, guiding cosmic rays toward regions where instruments await their arrival. At these altitudes, the spacecraft also encounters an unexpected phenomenon. The sudden increase in cosmic ray flux can temporarily overwhelm some detectors, requiring real-time adjustments to filter out noise and maintain signal integrity. Far from the surface, where temperatures plummet to as low as -85 degrees Celsius, these detectors must withstand conditions that challenge even the most advanced technologies. They are designed not only to survive, but also to function optimally in an environment so cold it rivals some of the coldest places known in the universe, places like the Boomerang Nebula, which holds the record for being colder than deep space itself. These instruments work tirelessly, sifting through a deluge of cosmic radiation and background noise, seeking out faint signals from dark matter particles that may have been traveling for billions of years before reaching this edge of Earth's gravitational influence. The journey of these detectors involves precise calibration. Each instrument undergoes at least 120 adjustments to account for temperature fluctuations and the varying levels of cosmic radiation encountered during ascent. In the realm of extreme altitudes, the presence of dark matter is not just a theoretical concept, but an active area of scientific exploration. Instruments at the edge of space provide a vantage point where researchers can test theories about particle interactions that occur far beyond the reach of ground-based detectors. The journey through Earth's upper atmosphere and into space marks more than a physical transition. It represents a leap into understanding some of the most profound mysteries of our universe. Here, at the threshold between Earth and the vast cosmos, humanity stands poised to unlock secrets that have eluded us for centuries, all within reach of instruments designed for such extraordinary conditions. At approximately 100 kilometers above Earth's surface, the atmospheric pressure drops to about 3/10,000ths of a pascal, an environment far more extreme than that inside even the most pressurized aerosol can. Here, each molecule of air is so sparse it no longer interacts in familiar ways, floating almost independently through the vacuum. This thinning atmosphere marks the Kármán line, where Earth's gravity still holds significant sway, but aerodynamic flight becomes impossible without rocket propulsion. The thermosphere, extending from about 80 to 600 kilometers above sea level, is a dynamic layer characterized by its rapid temperature fluctuations and extreme density variations. In this region, cosmic rays bombard objects with increased intensity, their energy levels rising as they penetrate deeper into the upper atmosphere. These high-speed particles, primarily protons and atomic nuclei, originate from distant corners of the universe, traveling at velocities close to the speed of light. Their interaction with Earth's upper layers provides critical insights into stellar processes that occurred billions of years ago, before life evolved on our planet. This bombardment not only challenges spacecraft, but also offers a window into the cosmos' ancient history. The thermosphere is paradoxically both extremely hot and cold at the same time. Solar radiation heats gas molecules to extraordinary temperatures here, yet because these gases are spread out over distances of about 10 kilometers between individual particles in such thin air, they create an environment of extreme temperature contrasts. This layer not only supports space exploration, but also reveals fascinating insights into atmospheric physics. The density is so low, about 1/1,000,000th of what it is at sea level, that conventional aircraft cannot generate enough lift to maintain flight. Billions of years ago, volcanic eruptions were a key factor in shaping early Earth's atmosphere by releasing gases like carbon dioxide and nitrogen. These initial conditions laid the foundation for what would become one of the most critical layers necessary for life, the oxygen-rich air we breathe today. This gradual transformation over time has created the atmospheric shield that now facilitates space exploration. As spacecraft pass through the thermosphere, they encounter a layer where high-energy particles from solar flares bombard with increased intensity. At this altitude, the density is so low, about 1/1,000,000th of what it is at sea level, that conventional aircraft cannot generate enough lift to maintain flight. This thinning air not only allows for such velocities, but also highlights how natural processes have created an environment seemingly hostile, yet essential for human presence. The Kármán line marks a threshold where Earth's atmosphere transitions into the vacuum of space. At approximately 100 kilometers above sea level, temperatures can drop as low as -85 degrees Celsius. This extreme cold presents challenges not just for equipment, but also for understanding how materials behave under such conditions. The boundary is also characterized by significant changes in pressure and density, which create unique stresses on spacecraft structures. These factors contribute to the intense vibrations and shaking experienced by spacecraft as they pass through this layer. The thermosphere's dynamic nature is further exemplified by its role in radio communication. This layer reflects and refracts radio waves back toward Earth's surface, enabling global communication networks. The ionization of gases due to solar radiation creates a complex environment where signals can be both enhanced and disrupted. Understanding these processes is crucial for maintaining reliable communication links between ground stations and satellites orbiting at the edge of space. The gradual increase in oxygen levels through photosynthesis has been fundamental for both human survival on Earth and our capacity to venture into space. Over billions of years, this process transformed early Earth's atmosphere from an inhospitable mixture of gases to one rich in breathable air. This atmospheric evolution is a testament to how natural processes can create conditions necessary not just for life, but also for exploration beyond our planet's surface. At an altitude of approximately 100 kilometers above Earth's surface, a spacecraft breaches the Kármán line, marking its entry into space. The atmospheric pressure drops to about 3/10,000ths of a pascal, and each molecule of air floats almost independently in this near-vacuum environment. This boundary is not just a threshold, but a point where aerodynamic forces cease to play a significant role, allowing for the possibility of orbit without constant propulsion adjustments. For spacecraft, crossing this line means entering an area where conventional aircraft cannot sustain flight due to the extreme thinness of the air. The moment a satellite crosses the Kármán line, it leaves behind the thermosphere's dynamic temperature fluctuations and enters into true space, where temperatures can plummet to as low as degrees Celsius. This cold is not merely a drop in ambient warmth, but an absence of atmospheric insulation that would otherwise retain heat near Earth's surface. The satellite experiences this profound chill as its instruments adapt to the extreme conditions, highlighting the remarkable engineering required for such missions. In contrast, deep within our planet's core, temperatures can reach over 6,000 degrees Celsius, hotter than the surface of the Sun, a stark reminder of the varied extremes encountered in different environments. As the spacecraft crosses this boundary, it encounters a sudden increase in cosmic ray bombardment, which rises by about 2.8 times compared to sea level on Earth. These high-energy particles, primarily protons and atomic nuclei, originate from distant corners of the universe, traveling at velocities close to the speed of light. The satellite's sensors detect these collisions, each one a testament to the immense energy that exists in deep space. This increase in radiation exposure presents both challenges for spacecraft design and opportunities for scientific discovery, offering insights into cosmic phenomena far beyond Earth's protective atmosphere. At this altitude, sound cannot propagate because there are no molecules to carry pressure waves. The vacuum is not just an absence of noise, but a profound shift in how information travels through space. In this environment, Communication relies on electromagnetic radiation, radio waves and light, which can travel unimpeded across vast distances. However, the spacecraft must also contend with occasional bursts of solar wind particles that disrupt signal integrity, requiring complex error correction algorithms to maintain reliable contact with Earth. Once past the Kármán line, the spacecraft enters an environment where microgravity reigns supreme. Here, objects float freely due to the lack of significant gravitational pull from Earth's surface. The satellite experiences a brief period of intense vibration and shaking as it passes through the thermosphere, which occurs around 8,600 kilometers above Earth's surface. This transition is not just physical, but also marks a change in the spacecraft's operational parameters, requiring adjustments to its systems for optimal performance in space. Each adjustment is a critical step toward ensuring the satellite can function effectively in this unique environment. As the spacecraft crosses the Kármán line, it leaves behind Earth's protective magnetic field and atmospheric layers, exposing itself to increased cosmic radiation. Instruments aboard detect particles from distant stars and galaxies, offering a glimpse into the violent processes that shape the cosmos. Each collision with these high-energy particles is a reminder of the immense energy that exists in deep space. This heightened exposure presents both challenges for spacecraft design and opportunities for scientific discovery, providing valuable data on cosmic phenomena far removed from Earth's protective embrace. Beneath the spacecraft, Earth's blue curvature slowly recedes, its surface a delicate arc against the infinite blackness of space. At this altitude, about 100 kilometers above sea level, the boundary known as the Kármán line marks where Earth's atmosphere becomes too thin to sustain aerodynamic flight. The pressure here is a mere 3/10,000ths of what we experience on the surface, yet this vacuum feels more like a palpable presence than an absence. Each molecule of air floats almost independently, barely interacting with its neighbors in this near-vacuum environment. This vast emptiness contrasts sharply with Earth's familiar blue below, a color that once seemed infinite, but is now seen as a finite boundary. The curvature of the planet diminishes into perspective, reminding us that what we consider, the sky, is merely a thin layer of gases enveloping a watery sphere. Yet, even in this vacuum, life on Earth thrives because of its unique atmosphere, an envelope that holds together the conditions necessary for life. The spacecraft experiences a sudden push as it transitions into space, a jolt attributed to the abrupt cessation of aerodynamic forces and the increase in cosmic ray bombardment. These high-energy particles are remnants from supernova explosions throughout the universe, traveling at near-light speeds. They penetrate even this thin layer of atmosphere, their energy increasing by about 2.8 times compared to sea level. This radiation would be lethal without the protection of Earth's magnetic field and atmosphere below. The spacecraft now enters a realm where sound cannot propagate, as there are no molecules to carry pressure waves, echoes of human-scale physics fading into the cosmic silence. As the craft ascends beyond this boundary, it encounters conditions that challenge our understanding of what it means to be in space. At 28,000 kilometers per hour, or Mach 30, the spacecraft must overcome Earth's gravitational pull, a force that diminishes with distance but never truly vanishes. The temperature at this edge can plummet to as low as degrees Celsius due to the lack of atmospheric insulation, colder than most places on Earth's surface. Yet, paradoxically, the coldest place in the known universe is not here, nor in any deep space vacuum, but in a laboratory on Earth, where temperatures approach absolute zero under controlled conditions. The spacecraft now finds itself in an environment where conventional aircraft could never fly without rocket propulsion. The density of air at this altitude is about 1/1,000,000th that at sea level, making it extremely difficult for aerodynamic forces to generate lift. This thin layer of atmosphere serves as a fragile shield against the harshness of space. Cosmic rays and solar radiation bombard Earth's surface with increased intensity here. Despite this vulnerability, Earth remains a life-sustaining oasis in an otherwise hostile cosmic environment. The spacecraft continues its journey upwards, leaving behind the blue curve of our planet for the endless black beyond. The view from 100 kilometers above Earth is both awe-inspiring and humbling. Below lies the familiar watery sphere, now seen as a finite boundary against the vastness of space. This altitude marks where Earth's atmosphere thins to near vacuum, an environment far more extreme than even the most pressurized aerosol can. Here, each molecule of air floats almost independently, barely interacting with its neighbors. The spacecraft experiences a brief period of intense vibration and shaking as it passes through the thermosphere, which extends from about 80 to 600 kilometers above Earth's surface. This layer is where the atmosphere transitions from aerodynamic forces to the realm of rocket propulsion, marking the true edge of space. At an altitude of approximately 100 kilometers, spacecraft encounter a dramatic shift as they breach the Kármán line. Here, atmospheric pressure drops to about 3/10,000ths of what we experience at sea level, and each molecule of air floats almost independently in this near-vacuum environment. This boundary marks where Earth's atmosphere becomes too thin for aerodynamic flight. Yet, it is also a place where cosmic phenomena like geomagnetic storms connect directly with the planet's surface through auroras, bridging the vastness of space with Earth's atmospheric layer. The temperature at this edge can plummet to as low as degrees Celsius due to the lack of atmospheric insulation. This extreme cold is not just a consequence of thin air. It also plays a crucial role in the formation of auroras. As charged particles from solar winds interact with atoms in Earth's upper atmosphere, they excite electrons to higher energy states. When these excited electrons return to their ground state, they emit photons that we perceive as the colorful displays of light known as auroras. This process highlights how even in the coldest place near Earth, life-sustaining processes are intricately linked with cosmic events. Spacecraft must travel at least 28,000 kilometers per hour to overcome Earth's gravitational pull and reach space. As they pass through this boundary, astronauts often report feeling a significant push or jolt due to the sudden change in atmospheric drag. This sensation is not just physical, but also marks the transition from suborbital flight into true space travel. The shift in pressure and temperature at the Kármán line can be so abrupt that it affects the spacecraft structure, causing vibrations that astronauts experience as a noticeable jolt. Yet, this momentary disturbance underscores the dynamic interaction between Earth's atmosphere and the vacuum of space. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles are not just random occurrences, but part of an ongoing cosmic process. They originate from distant stars and even more ancient supernovae explosions, traveling through the universe at velocities close to the speed of light. When these particles interact with Earth's magnetic field, they can cause geomagnetic storms that lead to auroras. This connection between deep space phenomena and visible lights on Earth illustrates how events billions of years old continue to influence our planet today. The density of air is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. Yet, this thin layer of atmosphere plays a critical role in the formation of auroras. The interaction between solar wind particles and atoms in the upper atmosphere creates a cascade of charged particles that spiral along magnetic field lines toward Earth's poles. As these particles collide with atmospheric gases like oxygen and nitrogen, they produce the vibrant colors seen in auroras. This process demonstrates how even in an environment where conventional flight is impossible, life-sustaining processes remain active. Spacecraft experience a brief period of intense vibration and shaking as they pass through the thermosphere, which occurs around 80 to 600 kilometers above Earth's surface. These vibrations are not just mechanical, they also signify the transition from aerodynamic forces to microgravity. The sudden change in atmospheric drag can be felt by astronauts as a significant push or jolt. This momentary disturbance underscores how even at the edge of space, where conventional flight is no longer possible, the boundary between Earth and the cosmos remains dynamic and ever-changing. At an altitude of 100 kilometers above Earth's surface, a spacecraft passes through the Kármán line, where atmospheric density drops dramatically. Here, each molecule of air floats almost independently, with distances between them far greater than the molecules would like. The pressure is now so low that it measures about 32/10,000ths of a pascal, an environment far harsher than the interior of even the emptiest vacuum chamber on Earth. This thinning atmosphere marks the beginning of space, where the protective layer surrounding our planet gradually fades into the void. Yet, this is not just the end of aerodynamic flight. It's also the start of a process that will eventually strip away much more than mere air. This boundary layer signifies the start of a long-term trend. As Earth ages, its atmosphere continues to thin over billions of years due to solar winds and particle interactions. The sun's radiation pressure pushes gas atoms away from our planet at an average speed of about 400 kilometers per second. Over time, This relentless force will slowly erode the protective layer that now shelters life on Earth's surface. Astonishingly, even though the rate of loss seems negligible today, it amounts to thousands of tons of atmosphere escaping into space each year, a phenomenon that has been occurring since before humans first walked upright. This continuous erosion suggests that in 1 billion years, Earth's atmospheric pressure could drop significantly, affecting climate and habitability. At this altitude, spacecraft experience a brief period of intense vibration as they pass through the thermosphere, which extends from about 80 to 600 kilometers above sea level. The density of air is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. This thinning atmosphere also affects the behavior of radio waves crucial for communication with Earth-bound stations. In the thermosphere, ionized particles reflect certain frequencies back toward the surface, enabling global communication networks and GPS systems. However, beyond this boundary, signals can become weaker or lost entirely as fewer molecules are available to carry them. Beyond the Kármán line, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles, primarily protons and atomic nuclei, originate from distant corners of the universe, traveling at velocities close to the speed of light. The increased exposure to these rays has implications for spacecraft design and astronaut health, necessitating robust shielding to protect against radiation damage. This heightened radiation environment underscores the challenges faced by future space exploration missions as they venture further into the cosmos. The thinning atmosphere also impacts Earth's climate system over geological timescales. As more gases escape into space, the greenhouse effect weakens, leading to a gradual cooling of the planet. Eventually, this could lead to conditions similar to those on Mars, a world with a thin carbon dioxide envelope and extreme temperature swings. This process highlights how Earth's geology, solar activity, and atmospheric dynamics are interconnected in ways that shape our planet's future habitability. While we focus on the immediate effects at the Kármán line, it is worth considering what this edge represents for future generations. As Earth's protective blanket continues to thin over billions of years, the conditions necessary for life will shift dramatically. Eventually, our planet may lose enough atmosphere to resemble Mars, a world with a thin carbon dioxide envelope and extreme temperature swings. This gradual transition underscores the interconnectedness between Earth's geology, solar activity, and atmospheric dynamics, providing insights into the conditions required for life as we know it across the universe. As you ascend towards the edge of space at an altitude of 100 kilometers, a remarkable transformation unfolds over vast timescales. Here, atmospheric pressure drops to less than 3/10,000ths of a pascal. This is where spacecraft feel a significant push or jolt as they transition from suborbital flight into space. 1 billion years ago, this region would have been far more hospitable, with denser air capable of sustaining higher temperatures and greater friction against incoming debris. Today's near-vacuum environment contrasts sharply with the dense atmosphere that once swirled around Earth like a protective blanket. In a billion years, this zone might be even thinner as Earth's gravitational pull weakens by approximately 10% over time, further diminishing its ability to retain gases. The temperature at this edge can plummet to degrees Celsius due to the lack of atmospheric insulation. Yet, paradoxically, this frigid region once hosted warmer conditions that facilitated complex chemical reactions essential for life's origins on Earth. These reactions occurred in a much denser atmosphere where molecules collided more frequently, unlike today's sparse environment. Over time, solar radiation and particle interactions gradually thinned out the upper layers of our atmosphere, cooling it significantly. Looking forward another billion years, this region may become even colder as the sun continues to evolve into a red giant, further reducing atmospheric density. The density of air is about 1/1,000,000th that at sea level, making it extremely difficult for conventional aircraft to maintain lift without rocket propulsion. This extreme thinness is not just a barrier to flight, but also a testament to the delicate balance maintained by Earth's atmosphere over billions of years. In the distant past, this region would have been thick with gases, providing more resistance against incoming cosmic particles and meteoroids. Over time, however, solar winds and other factors slowly eroded the upper layers of our atmosphere, leading to its current state. Looking forward a billion years, further thinning may occur as Earth's magnetic field weakens by approximately 20%, potentially exposing life forms on the surface to greater radiation risks. Astronauts have reported feeling a significant push or jolt when transitioning from suborbital flight into space, which can be attributed to the sudden change in atmospheric drag. This sensation is akin to being abruptly released after holding onto something tightly, both disorienting and exhilarating. From an evolutionary perspective, this experience is incredibly recent. It was only with the advent of spacecraft that humans could feel such a transition firsthand. A billion years ago, there would have been no human observers to witness these changes at the edge of space. In another billion years, if humanity persists, we may look back on this moment as one of many critical thresholds in our exploration of the cosmos. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles originate from distant parts of the universe and interact with atoms in the upper atmosphere, creating showers of secondary particles. The increased exposure to these rays can cause radiation damage to spacecraft materials over time. Interestingly, this bombardment also plays a role in atmospheric chemistry by producing ions that contribute to the formation of noctilucent clouds, rare ice crystals that form at extremely high altitudes under specific conditions. As Earth's magnetic field weakens, cosmic ray exposure may increase further, potentially affecting satellite operations and space travel. However, some scientists predict that as Earth's magnetic field weakens, it could also lead to unexpected changes in the ionosphere, possibly creating new types of auroras or altering global communication systems. Spacecraft experience a brief period of intense vibration and shaking as they pass through the thermosphere, which occurs around 8,600 kilometers above Earth's surface. This turbulence is caused by fluctuations in atmospheric density and temperature gradients within this layer. The vibrations can be uncomfortable for astronauts, but are necessary to break free from aerodynamic forces that keep aircraft grounded. In contrast, ancient civilizations would have experienced a much more stable atmosphere at these altitudes due to higher air pressure and denser molecular interactions. As Earth continues its journey through time, the thermosphere will likely become even less hospitable, with reduced gas density making it increasingly challenging for spacecraft to maintain their trajectories without significant fuel consumption. As a spacecraft ascends past 80 kilometers, it encounters the Van Allen radiation belts, donut-shaped regions encircling Earth where charged particles are trapped by magnetic fields. These belts can extend from about 60 to 55,000 kilometers above our planet's surface, acting as a formidable shield against solar and cosmic radiation. The particles within these belts move at incredible speeds, some reaching up to 99% the speed of light. Yet they pose significant risks for satellites orbiting in this region. The Van Allen belts are composed of two main regions: the inner belt, starting about 1,000 kilometers above Earth's surface, and the outer belt, which begins around 10,000 kilometers out. The inner belt is more densely packed with protons and electrons, while the outer belt contains a higher concentration of energetic electrons. These particles can damage sensitive electronics aboard satellites, sometimes leading to permanent failures or temporary glitches known as single-event upsets. Despite their protective function for life on Earth's surface, they present a formidable challenge for spacecraft navigating through them. Within these belts, protons in the inner belt possess an average kinetic energy of approximately 30 million electron volts. This is equivalent to the energy that could be stored by a small battery, but concentrated into subatomic particles. The intensity of radiation peaks at altitudes between 2,000 and 7,000 kilometers, creating a hazardous environment for satellites. Interestingly, this same radiation belt that endangers satellites also provides a valuable service. It shields Earth from potentially lethal doses of cosmic rays and solar wind. For instance, the inner belt's protons are so energetic they can penetrate spacecraft shielding, causing damage over time. Astronauts venturing beyond the Kármán line are protected by their spacecraft shielding, which is designed to withstand these intense particle bombardments. However, prolonged exposure to such radiation could lead to health issues for astronauts on extended missions. This underscores the delicate balance between protection and risk in space exploration. Meanwhile, satellites must navigate a path that minimizes exposure while still achieving their objectives. During periods of high solar flare activity, additional particles are injected into these regions, temporarily enhancing their strength and complexity. Conversely, during quieter solar cycles, some of this trapped energy can be gradually lost to Earth's upper atmosphere, reducing the overall intensity of the radiation belts. This dynamic interplay between solar winds and Earth's magnetic field continues to shape our understanding of space weather phenomena. For example, a single solar flare can inject enough particles into the Van Allen belts to increase their mass by several tons in just hours. The Kármán line at approximately 100 kilometers above Earth's surface marks, where atmospheric pressure drops to about 3/10,000ths of a pascal. Here, each molecule of air floats almost independently, with distances between them far greater than the molecules would like. This thinning atmosphere is crucial for spacecraft, as it allows them to achieve orbit without excessive drag. However, this same environment poses challenges for maintaining satellite operations over long periods due to radiation and micrometeoroid impacts. At an altitude of approximately 100 kilometers, a spacecraft encounters a boundary where Earth's atmosphere becomes too thin to sustain aerodynamic flight. This is known as the Kármán line, named after Theodor von Kármán in 1957. Here, atmospheric pressure drops to about 3/10,000ths of a pascal, and each molecule of air floats almost independently in this near-vacuum environment. Beyond this point, spacecraft experience a significant push or jolt as they transition from suborbital flight into space. This sensation is not caused by any wind, but rather the sudden change in atmospheric drag. Just beyond this boundary lies an unexpected neighbor, space debris orbiting just above the edge of Earth's atmosphere. At this altitude, objects like defunct satellites and spent rocket stages can remain in orbit for decades due to the minimal air resistance. The density of air is about 1/1,000,000th that at sea level, making it extremely difficult for conventional aircraft to maintain lift without rocket propulsion. This thin layer acts as a transitional zone where debris can linger longer than expected before eventually falling back into Earth's atmosphere. Spacecraft traveling through this region experience an increase in cosmic particle interactions by approximately 2.8 times compared to sea level on Earth. These high-energy particles, primarily protons and atomic nuclei, originate from distant corners of the universe, traveling at velocities close to the speed of light. As satellites pass through this zone, these particles can trigger a phenomenon known as single-event upsets, where individual bits in memory systems are flipped. This unexpected occurrence highlights how space debris not only poses a mechanical threat, but also an electromagnetic one that could disrupt vital communication systems. At approximately 100 kilometers above Earth's surface, temperatures plummet to as low as degrees Celsius due to the lack of atmospheric insulation. In this environment, water cannot exist in liquid form because the temperature is too low and there's insufficient atmospheric pressure to maintain it. This extreme cold can cause materials on satellites or spacecraft to contract, potentially leading to structural issues over time. The paradox here is that while space itself is often associated with vast expanses of emptiness, this thin layer near Earth's atmosphere presents one of the coldest environments known in our solar system. Space debris at these altitudes includes remnants from early nuclear tests conducted high above Earth, such as those performed decades ago. These objects can remain in orbit for years before gradually re-entering the atmosphere due to atmospheric drag and gravitational forces. The iron in your blood was forged in a star that died before our sun existed, yet it now finds itself part of space debris circling Earth. This connection between cosmic events billions of years old and modern-day technology underscores the intricate web of celestial processes that shape our universe. As spacecraft pass through this region, they experience intense vibrations and shaking due to the thermosphere's dynamic conditions around 8,600 kilometers above Earth's surface. These vibrations are a result of the sudden change in aerodynamic forces as the craft transitions into space. This brief period of turbulence can be felt by astronauts aboard spacecraft, providing a physical reminder of their journey from Earth's atmosphere to the vastness beyond. The unexpected presence of debris at this altitude serves as a constant reminder of humanity's expanding influence on the cosmos and the challenges we face in managing our orbital environment. At near-space altitude, approximately 100 kilometers above Earth's surface, atmospheric pressure drops to about 3/10,000ths of a pascal. Each molecule of air floats almost independently in this near-vacuum environment, making it impossible for human lungs to function without a pressurized suit. The temperature can plummet to as low as degrees Celsius due to the lack of atmospheric insulation. In such conditions, even simple movements become fraught with danger. Any sudden jump or uncontrolled movement could lead to rapid decompression sickness and severe bodily harm. Spacecraft traveling this altitude experience intense vibration and shaking as they pass through the thermosphere. This turbulence is not caused by wind or air currents, but rather the abrupt change in atmospheric drag. The Kármán line marks the boundary where Earth's atmosphere becomes too thin for conventional aircraft to sustain flight without rocket propulsion. Astronauts have reported feeling a significant push or jolt when transitioning from suborbital flight into space, an effect that can be disorienting if not anticipated. This sensation is akin to being propelled away by an invisible force, highlighting the stark contrast between Earth's atmosphere and the vacuum of near space. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles can cause damage to electronic systems and biological tissues alike. The increased radiation exposure poses additional risks for anyone venturing into this environment unprotected. Despite the harsh conditions, it is here that humanity pushes its boundaries, exploring realms where life as we know it cannot survive without artificial assistance. The edge of space offers both a tantalizing promise and a stark warning for those who dare to explore without protection. The density of air at near-space altitude is about 1/1,000,000th that at sea level, making it extremely difficult for aircraft to maintain lift without rocket propulsion. This thinness means that any attempt to move freely would result in immediate exposure to the vacuum, leading to rapid decompression and loss of consciousness within seconds. The human body, unaided by a pressurized suit, cannot survive these conditions due to the extreme lack of atmospheric pressure. In this environment, water cannot exist in liquid form because the temperature is too low, and there's insufficient atmospheric pressure to maintain it. At an altitude of approximately 100 kilometers, spacecraft must travel at least 28,000 kilometers each to overcome Earth's gravitational pull. This speed ensures that they can escape the planet's atmosphere and enter space. The sudden transition from suborbital flight into space is marked by a significant push or jolt experienced by astronauts. This phenomenon occurs due to the rapid decrease in atmospheric drag as the spacecraft reaches the Kármán line. The intense vibration and shaking during this period highlight the dynamic nature of the boundary between Earth's atmosphere and the vacuum of space. In this environment, sound cannot propagate because there are no molecules to carry pressure waves. Any attempt by a human to shout or communicate would be futile, as their voice would not travel beyond their lips in the near-vacuum conditions. The lack of air resistance also means that any object thrown would continue moving at a constant velocity until it encounters another force, such as re-entry into a denser atmosphere layer. This illustrates the fundamental difference between Earth's surface and near space, where familiar physical laws are significantly altered by the extreme environmental conditions. At an altitude of approximately 100 kilometers above Earth's surface, a spacecraft reaches the Kármán line, where atmospheric pressure drops to about 3/10,000ths of a pascal. Here, each molecule of air floats almost independently in this near-vacuum environment, creating conditions far more extreme than those inside even the most pressurized aerosol can. As the spacecraft ascends, it encounters a region bombarded by solar radiation, yet paradoxically, temperatures plummet to as low as degrees Celsius due to the lack of atmospheric insulation. This coldness is not merely a result of altitude, but a consequence of how little air there is to retain heat. The thermosphere, despite being bathed in intense sunlight, experiences extreme cold because it lacks sufficient molecules to transfer and retain that energy. Each molecule floats so far apart that they barely interact, let alone share heat effectively. This environment contrasts sharply with the cozy warmth we experience on Earth's surface, where air molecules are dense enough to trap heat efficiently. In space, this thinness means temperatures can drop to levels unimaginable in our everyday lives. Yet paradoxically, just a few kilometers closer to Earth, it would be much warmer due to atmospheric insulation. As the spacecraft crosses the Kármán line, it experiences a significant push or jolt caused by the sudden change in atmospheric drag. This moment marks not only a physical transition, but also a psychological one for astronauts, as they feel the boundary between Earth and space. The pressure drop is so dramatic that water would instantly vaporize if present, highlighting just how thin this layer of atmosphere truly is. Yet, despite the intense solar radiation bombarding this region, it remains cold due to the lack of molecules to transfer heat effectively. Cosmic rays bombard objects at a rate about 2.8 times higher here compared to sea level on Earth. These high-energy particles penetrate deep into spacecraft materials, creating showers of secondary particles and posing significant challenges for both technology and human health. The paradox lies in how this region, so exposed to the sun's radiation, remains cold due to its thinness and lack of thermal conductivity. This bombardment is relentless, yet it fails to warm the environment significantly because there are too few molecules to share that energy. Additionally, at these altitudes, the ionization levels reach a maximum, creating an electrically charged layer around Earth known as the ionosphere, which can interfere with radio signals and create auroras visible from the ground. At this altitude, conventional aircraft cannot fly without rocket propulsion, as aerodynamic forces no longer function effectively in such a sparse atmosphere. The density of air here is about 1/1,000,000th that at sea level, making lift nearly impossible for traditional planes. In practice, an airplane would need to travel at speeds exceeding Mach 5 to generate sufficient lift, which is impractical without rocket engines. Yet the spacecraft continues its journey, experiencing a brief period of intense vibration and shaking as it passes through this layer. This turbulence is not caused by wind or fluid resistance, but rather by the sudden change in atmospheric drag. The environment here is so extreme that even sound cannot propagate due to the lack of molecules to carry pressure waves. The thermosphere's paradoxical coldness, despite being bombarded by solar radiation, highlights a fundamental property of our atmosphere: its ability to retain heat through molecular interactions. This thin layer acts as both a barrier and an enigma, protecting Earth from harmful cosmic rays while remaining surprisingly cold due to its sparse nature. As the spacecraft continues its ascent beyond this boundary, it leaves behind not just air, but also the peculiarities of a world where extreme radiation meets paradoxical chill, illustrating the delicate balance that sustains life on our planet. At an altitude of approximately 100 kilometers, a spacecraft encounters the Kármán line, where Earth's gravitational pull begins to noticeably weaken. Here, gravity diminishes from its full strength at sea level to just 1% of that force. The sudden reduction in atmospheric drag causes a jolt felt by astronauts as they transition into space. This boundary marks not only the edge of our atmosphere, but also the threshold for achieving true orbital velocity. The weakening gravity at this altitude affects more than just spacecraft. It influences how objects behave and interact. For instance, water cannot exist in liquid form due to both the extreme cold, reaching as low as -85 degrees Celsius, and the lack of atmospheric pressure. This environment is so harsh that each molecule of air floats almost independently, creating a near vacuum where conventional aerodynamics cease to apply. The density of air here is about 1/1,000,000th what it is at sea level, making lift impossible for aircraft without rocket propulsion. Beyond the Kármán line, cosmic rays bombard objects with increased intensity, roughly 2.8 times more than at Earth's surface. These high-energy particles originate from distant parts of the universe and travel through space at nearly the speed of light. They interact with atoms in the upper thermosphere, creating a cascade of secondary particles that can be detected by instruments aboard satellites. This bombardment underscores the dynamic nature of this region, where cosmic influences are more pronounced than terrestrial ones. At 100 kilometers above Earth's surface, the temperature plummets to an extreme level due to the absence of atmospheric insulation. The coldness here is so intense that it rivals some of the coldest temperatures recorded on our planet. Yet paradoxically, this region is also where spacecraft experience a brief period of intense vibration and shaking as they pass through the thermosphere's upper layers. This turbulence results from the sudden change in aerodynamic forces rather than any external disturbance. The push astronauts feel when crossing the Kármán line can be attributed to the rapid decrease in atmospheric density. As a spacecraft ascends, it must overcome Earth's gravitational pull by traveling at least 28,000 kilometers per hour, Mach 30. This speed is necessary not only to escape gravity, but also to maintain orbit once beyond the atmosphere's grasp. The energy required for this feat highlights the immense power of Earth's gravitational field and its gradual weakening with distance. In this near-vacuum environment, sound cannot propagate because there are no molecules to carry pressure waves. However, the absence of sound does not mean silence. Instead, it creates a profound emptiness that can be felt rather than heard. The isolation here is absolute, offering an eerie contrast to the vibrant soundscape we experience on Earth. This extreme quietness serves as a stark reminder of how different space truly is from our familiar world. At this altitude, the density of air has diminished to about 1/1,000,000th that at sea level, making it nearly impossible for conventional aircraft to maintain lift without rocket propulsion. This thinness affects not just flight, but also how objects behave in space. For instance, a feather and a hammer would fall at the same rate here due to the negligible influence of aerodynamic drag, demonstrating Galileo's principle in an environment where gravity alone governs motion. The feather, once buoyant on Earth, now behaves like any other object under the sole influence of gravitational forces. The weakening pull of gravity also means that astronauts experience a significant reduction in their perceived weight as they move beyond the Kármán line. This phenomenon is not just a matter of feeling lighter, but reflects a fundamental shift in how mass and distance interact with Earth's gravitational field. The force exerted by gravity decreases with the square of the distance from Earth's center, meaning that even small increases in altitude lead to noticeable changes in weight. For example, an astronaut weighing 70 kilograms at sea level might feel as light as a feather here, hovering almost effortlessly within their spacecraft. The temperature at this edge can plummet to as low as degrees Celsius due to the lack of atmospheric insulation. This extreme cold is not just a matter of discomfort. It affects the very materials that astronauts and spacecraft rely on for survival. Metals contract, plastics become brittle, and fluids freeze, each material responding uniquely to these harsh conditions. The temperature here can be likened to the coldest regions on Earth's surface. Yet the absence of atmosphere means there is no warmth to retain or distribute heat. Spacecraft must travel at least 28,000 kilometers per hour to overcome Earth's gravitational pull and reach space. This speed is not just a technical requirement, but a testament to the immense force of gravity that clings to objects near Earth's surface. At an altitude of approximately 100 kilometers, the ionosphere begins to play a crucial role in shaping how we perceive distant galaxies. Instruments aboard spacecraft detect electromagnetic waves from these far-off celestial bodies as they pass through this layer, acting like lenses that focus and filter signals. This process allows scientists on Earth to gather detailed information about stars and supernovae billions of light years away. The ionosphere's ability to reflect radio waves back to the surface is a phenomenon that quietly tilts our understanding of space communication, making it possible for us to listen in on the universe's most distant whispers. Beyond its role as a lens, the ionosphere also serves as a dynamic environment where charged particles interact with solar radiation. This interaction creates auroras and other atmospheric phenomena visible from Earth's surface. The temperature at this altitude can plummet to degrees Celsius due to the lack of insulation provided by thicker layers of air below. Instruments designed for space exploration must be robust enough to withstand these extreme conditions, ensuring that data collected remains accurate despite the hostile environment. As spacecraft breach the Kármán line, they experience a significant push or jolt caused by the sudden change in atmospheric drag. This moment marks the transition from suborbital flight into true space. The ionosphere, with its varying density and electrically charged particles, influences this boundary layer's behavior. Instruments aboard are calibrated to measure these changes precisely, providing insights into how Earth interacts with the cosmos at this critical altitude. The thinning air here is so sparse that each molecule floats almost independently in a near-vacuum environment. At an altitude of 100 kilometers, cosmic rays bombard objects at a rate nearly 3 times higher than at sea level on Earth. These high-energy particles originate from distant stars and galaxies, traveling through space before reaching our planet's upper atmosphere. The ionosphere plays a vital role in shielding us from these harmful radiation bursts by scattering them across the sky. Instruments designed to detect cosmic rays can measure their intensity and direction, offering clues about the origins of these energetic particles and how they influence Earth's environment. The density of air at 100 kilometers above sea level is about 1/1,000,000th that at sea level on Earth, making it extremely difficult for conventional aircraft to maintain lift. Instruments aboard spacecraft must be capable of operating in this near-vacuum environment, where the lack of pressure requires specialized equipment and techniques. The ionosphere's role extends beyond just reflecting radio waves. It also influences how these high-altitude instruments function by affecting their thermal properties and electromagnetic fields. This thin layer acts as a crucial interface between Earth's atmosphere and the vastness of space. Instruments designed to detect electromagnetic waves from distant galaxies are finely tuned to operate in the ionosphere's unique conditions. They must account for the sudden changes in pressure, temperature, and particle density that occur at this altitude. These devices can reveal the faintest signals from the farthest reaches of the universe, allowing us to study stars and galaxies billions of light years away. The data collected here provides a window into the cosmos, offering insights into the formation and evolution of our galaxy and others like it. This delicate balance between Earth's atmosphere and the vacuum of space is crucial for these instruments to function effectively. The cooling process of a meteorite after its fiery atmospheric entry is a complex interplay of physics and chemistry. As it plunges through Earth's atmosphere at speeds exceeding 28,000 kilometers per hour, the surface of the meteorite reaches temperatures hot enough to vaporize rock. Surprisingly, some small fragments can retain residual heat from re-entry even after cooling for minutes in the near vacuum of space, creating a thermal gradient that defies expectations. Despite this extreme cold, the surface of the meteorite remains relatively warm compared to its surroundings because it retains heat absorbed during re-entry. Specifically, the temperature difference between the surface and the immediate environment can be as high as 150 degrees Celsius, making direct contact with such an object potentially uncomfortable and even hazardous without proper protection. The iron within the meteorite, forged in a star that died before our sun existed, records cosmic history through its isotopic composition, highlighting the vast timescales involved in stellar evolution. The cooling process of a meteorite after its fiery atmospheric entry is a complex interplay of physics and chemistry. As it plunges through Earth's atmosphere at speeds exceeding 28,000 kilometers per hour, the surface of the meteorite reaches temperatures hot enough to vaporize rock. Yet within minutes of breaching the thermosphere, it begins to cool rapidly. At an altitude of approximately 100 kilometers, where atmospheric pressure drops to about 3.2x 10^4 pascals, the temperature can plummet to as low as degrees Celsius due to the lack of insulation from a dense atmosphere. At this altitude, the density of air is about 1/1,000,000th that at sea level, which means each molecule of nitrogen and oxygen moves with greater independence. This thinness affects how heat dissipates from the meteorite's surface, allowing it to cool more quickly than it would closer to Earth. The process of cooling also involves a delicate balance between radiation and conduction, as the meteorite radiates away its excess heat while simultaneously losing molecules to space. Imagine touching this cooled but still warm surface after re-entry. Your hand would feel an unexpected warmth on contact, despite the surrounding environment being extremely cold. This paradoxical sensation arises from the thermal inertia of the meteorite's material and the stark contrast with the near-vacuum conditions around it. The temperature difference between your skin and the meteorite could be as high as 150 degrees Celsius, highlighting the extreme range of temperatures encountered in this environment. As the meteorite continues its descent, cosmic rays bombard its surface at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles interact with the material of the meteorite, potentially altering its structure and composition over time. This interaction is part of an ongoing process that has been occurring for billions of years across countless celestial bodies in our universe. Each impact leaves a microscopic trace, contributing to the gradual erosion of the meteorite as it journeys through space. At an altitude of approximately 100 kilometers above sea level, a spacecraft encounters the Kármán line, where atmospheric pressure drops to less than 3/10,000ths of a pascal. Here, each molecule of air floats almost independently in this near-vacuum environment. This boundary not only marks the edge of space, but also plays a crucial role in climate change dynamics through its interactions with cosmic rays and other high-energy particles. These processes highlight the intricate connections between space and Earth's atmosphere, influencing global weather patterns and atmospheric chemistry. The upper thermosphere, which extends from about 80 to 600 kilometers above Earth's surface, is where temperatures can plummet to as low as degrees Celsius due to a lack of atmospheric insulation. This extreme cold contrasts with the intense heat generated by solar radiation at lower altitudes. Despite these frigid conditions, this layer is critical for reflecting and absorbing ultraviolet light from the sun, which helps regulate Earth's climate. The thermosphere's role in moderating incoming solar energy underscores how processes at the edge of space can have profound effects on our planet's weather systems. As spacecraft breach the Kármán line, they experience a significant push or jolt due to the sudden change in atmospheric drag. This phenomenon is not just a sensation for astronauts, but also a physical manifestation of Earth's gravitational pull weakening with altitude. At this boundary, gravity diminishes from its full strength at sea level to about 1% of that force. The energy required for spacecraft to reach and maintain orbit, 30,000 kilometers per hour, demonstrates the immense effort needed to overcome Earth's gravitational field. This transition highlights how human-made structures interact with natural forces on a scale far beyond our everyday experiences. Cosmic rays, high-speed particles from distant parts of the universe, bombard the upper thermosphere at an increased rate compared to sea level, about 2.8 times more intense. These energetic particles can ionize atoms in the atmosphere, creating a cascade of secondary particles that influence weather patterns and even affect climate change dynamics on Earth's surface. The interaction between cosmic rays and atmospheric gases can lead to cloud formation, which in turn affects global temperatures by either reflecting sunlight or trapping heat. This connection illustrates how events at the edge of space have direct implications for our planet's climate system. At an altitude of 100 kilometers, where spacecraft cross into space, the temperature plummets to as low as -85 degrees Celsius due to the lack of atmospheric insulation. In this environment, water cannot exist in liquid form. It either freezes or sublimates directly into vapor. The extreme cold and vacuum conditions at the Kármán line create an inhospitable environment for life as we know it. Yet, these harsh conditions also play a crucial role in regulating Earth's climate by influencing the formation of high-altitude clouds that can affect global weather patterns. This paradoxical relationship between space and climate underscores the intricate balance maintained by our planet's atmospheric layers. Beyond the Kármán line, spacecraft experience a significant push or jolt as they transition from suborbital flight into true space. This phenomenon is due to the sudden change in atmospheric drag, which ceases at this boundary. The intense vibrations and shaking felt during this transition are not just mechanical stresses, but also serve as a reminder of the delicate balance between Earth's atmosphere and the vacuum of space. These forces can influence satellite orbits and even affect the stability of spacecraft systems. Interestingly, these same upper atmospheric processes that cause such jolts in spacecraft also play a role in global weather patterns by affecting the distribution of heat within our planet's thinning outer layers. This connection highlights how events at the edge of space are deeply intertwined with Earth's climate system. At this altitude, temperatures can drop as low as -85 degrees Celsius due to the lack of atmospheric insulation. Cosmic rays entering this frigid region begin ionizing particles, creating tiny seeds that eventually grow into cloud droplets or ice crystals high in the atmosphere. This process, known as nucleation, is crucial for cloud formation and plays a vital role in regulating Earth's climate. Interestingly, these clouds formed by cosmic rays can reflect sunlight back into space, cooling our planet. The interaction between cosmic rays and atmospheric particles occurs at an astonishing rate, about 2.8 times more intense than at sea level on Earth. The Kármán line, marking the boundary of space at approximately 100 kilometers above sea level, is a critical threshold for this phenomenon. Here, spacecraft experience a brief period of intense vibration and shaking as they pass through the thermosphere, which extends from about 80 to 600 kilometers above Earth's surface. This turbulence is not just mechanical. It also marks a significant shift in atmospheric composition, where cosmic rays interact more freely with fewer molecules. The density of air at this altitude is roughly 1/1,000,000th that at sea level, making these interactions particularly efficient yet sparse. Each cosmic ray particle, primarily protons and atomic nuclei from distant stars or galaxies, travels through space at near-light speeds before colliding with Earth's upper atmosphere. These collisions initiate a chain reaction, producing secondary particles like muons and pions, which further interact with the remaining atmospheric gases. This process is akin to a microscopic fireworks display, where each collision sparks new particles that contribute to cloud formation in the upper atmosphere. The seeds for clouds are not just water vapor, but also these high-energy particles, which can ionize air molecules, facilitating the aggregation of aerosols and eventually leading to cloud droplets. The impact of cosmic rays on weather systems is subtle yet profound. By influencing cloud formation, they play a role in regulating Earth's albedo, the amount of solar radiation reflected back into space. Clouds act as mirrors, reflecting sunlight away from our planet, thereby cooling it down. Without the influence of cosmic rays, these clouds might form less frequently or differently, potentially altering weather patterns and climate over time. This connection between distant stars and Earth's weather is a reminder that we are part of an interconnected universe, where events billions of light years away can subtly shape our daily lives. At the edge of space, approximately 100 kilometers above sea level, Cosmic rays bombard particles with such intensity that they create showers of secondary particles. These high-energy collisions occur in the upper thermosphere, a region where the density of air is so low it barely registers on scientific instruments. Yet, despite this thinness, the thermosphere remains crucial for cloud formation and weather regulation. The temperature here can plummet to as low as -85 degrees Celsius, yet cosmic rays continue their relentless bombardment, indifferent to the extreme cold. This environment is a stark contrast to the warm, humid conditions necessary for cloud formation closer to Earth's surface. The journey of these cosmic, ray-induced particles from the thermosphere down to lower altitudes involves complex interactions with atmospheric gases. As they descend through layers of nitrogen and oxygen, these particles ionize molecules, creating charged ions that can act as seeds for cloud droplets. This process is crucial for understanding how weather systems on Earth are influenced by events occurring far beyond our planet's atmosphere. For instance, one study found that cosmic rays could increase the concentration of aerosols in the upper atmosphere by up to 30%, potentially leading to more frequent cloud formation at higher altitudes. These distant stellar deaths contribute to the formation of clouds here on Earth, linking us to the vastness of space in an unexpected and profound way. The process continues, with each collision adding another layer of complexity to the intricate dance between the heavens and our weather systems. The moment a spacecraft breaches the Kármán line at approximately 100 kilometers above Earth's surface, astronauts experience an abrupt sensation of weightlessness. This transition is not gradual but sudden, as if they have been thrust from one realm into another. The body, accustomed to gravity's constant pull, now floats free, unbound by familiar forces. Each breath becomes a conscious effort, the lungs adjusting to the thin atmosphere that offers little resistance. In this near-vacuum environment, the human body undergoes subtle changes. Blood no longer pools in the lower extremities, but instead redistributes throughout the torso and head, causing astronauts to experience facial puffiness and nasal congestion, a condition known as puffy face syndrome. This redistribution of fluids is a direct result of microgravity's influence on fluid dynamics within the body. Yet this sensation of weightlessness also offers an unexpected freedom. Muscles relax in ways they never do under Earth's gravity, leading astronauts to feel lighter than air itself. At the Kármán line, approximately 100 kilometers above Earth's surface, the human body undergoes a series of physiological changes as it transitions into microgravity. The inner ear fluids, which normally help maintain balance on Earth, now float freely inside the skull, causing disorientation and often leading to space adaptation syndrome, a condition characterized by nausea and dizziness in new astronauts. This sensation is akin to being upside down or spinning continuously, a feeling that can take days to acclimate to fully. Yet, once adapted, many astronauts report an overwhelming sense of freedom as their bodies adjust to the lack of weight pressing down on them. As they float, astronauts encounter temperatures that plummet to as low as degrees Celsius due to the lack of atmospheric insulation. This frigid environment contrasts sharply with the intense heat experienced during re-entry, where spacecraft can reach temperatures exceeding 1300 degrees Celsius. The extreme cold at this altitude is a reminder of how thin and fragile our atmosphere truly is. The same layer that keeps Earth warm acts as an insulating blanket for life on its surface. In space, without this protective shield, the temperature fluctuates wildly between day and night sides of objects, creating an environment where survival requires precise engineering. For instance, temperatures can swing from -85 degrees Celsius to over 100 degrees Celsius within just a few hours as spacecraft rotate in low Earth orbit. The sensation of weightlessness also affects how astronauts perceive time. Without the familiar pull of gravity, the body's internal clocks can become disoriented, leading to a phenomenon known as time dilation. This effect is most pronounced for those in orbit around Earth, where they experience slightly more time passing than someone on the planet's surface due to differences in gravitational fields. For astronauts at this altitude, every hour spent floating freely feels both timeless and fleeting, an odd duality that challenges our understanding of temporal flow. Specifically, astronauts aboard the International Space Station orbiting Earth at approximately 400 kilometers experience about 0.2 seconds more time per day than someone on the ground. The sudden absence of gravity also affects how objects move in this environment. In space, even small movements can result in significant changes in velocity due to the near-total vacuum and low drag forces. An object released from hand will float indefinitely unless acted upon by another force, such as a gentle push or collision with particles. This floating motion contrasts sharply with the predictable behavior of objects on Earth, where gravity and air resistance constantly influence their trajectories. Paradoxically, while space is often described as empty, it contains an abundance of tiny particles that can interact with spacecraft, causing unexpected nudges or impacts. As astronauts experience weightlessness for the first time, they also notice a peculiar shift in how sound behaves, or rather, doesn't behave. In this near-vacuum environment, sound waves cannot propagate because there are no molecules to carry pressure waves. The silence is profound and absolute, unlike any quietude experienced on Earth. This absence of sound can be disorienting for those accustomed to auditory cues that signal proximity or movement. Yet, the vacuum silence also offers a unique opportunity. It allows astronauts to communicate through radio waves without interference from background noise. This shift in communication methods underscores how space fundamentally alters our sensory experiences. The sensation of weightlessness extends beyond mere floating. It affects every bodily function and perception. Blood, no longer pulled downward by gravity, redistributes throughout the body, often causing a rush to the head. Astronauts may experience initial lightheadedness or even nausea as their vestibular system recalibrates. This adaptation is akin to learning to walk again after being bedridden for months. The human body, designed for life on Earth's surface, must now operate in an environment where gravity's influence is reduced to a fraction of its usual strength. In this new state, the heart no longer needs to work as hard against gravity, and fluids shift in ways that would be uncomfortable or even dangerous without proper training and equipment. At an altitude of approximately 100 kilometers, where spacecraft encounter the Kármán line, atmospheric pressure drops to about 3/10,000ths of a pascal. Here, each molecule of air floats almost independently in this near-vacuum environment. This boundary marks not just the edge of space, but also the beginning of a long-term transformation for Earth's atmosphere. Over billions of years, as solar radiation continues to strip away particles from our planet's upper layers, the thinning will accelerate. The process is gradual and relentless. In this zone, cosmic rays bombard objects at an increased rate compared to sea level on Earth, contributing to the erosion of atmospheric gases. This phenomenon, known as atmospheric escape, has been ongoing since Earth's formation. Yet, it is only now that we can measure its effects with precision. The total mass lost each year may seem insignificant, about 90 tons, but over billions of years, this steady leakage transforms the atmosphere from a thick protective blanket into something barely discernible. At these altitudes, temperatures plummet to as low as -85 degrees Celsius due to the lack of atmospheric insulation. This extreme cold plays a crucial role in the thinning process. The molecules themselves are so sparse that they no longer interact efficiently, leading to a gradual loss of heat and pressure. In this environment, water cannot exist in liquid form, nor can sound propagate through the near vacuum. Yet, paradoxically, it is here at the edge of space where life on Earth finds its most potent shield against cosmic radiation. The thinning atmosphere acts as an increasingly fragile barrier, allowing more high-energy particles to reach our planet's surface over billions of years. As we consider the future fate of Earth's atmosphere, one might wonder about the implications for our planet's climate and ecosystems. Over time, the upper layers will continue to dissipate into space, leaving only a residual envelope around Earth. This thinning process is not uniform. It occurs more rapidly at higher altitudes where molecules are less densely packed and have greater freedom to escape. The thermosphere, which extends from about 80 kilometers up to 600 kilometers above sea level, will be the first to see significant changes. Here, temperatures can plummet to as low as -85 degrees Celsius due to the lack of atmospheric insulation. This extreme cold accelerates the loss of gases like hydrogen and helium, which are lighter and more volatile than nitrogen or oxygen. At this altitude, cosmic rays bombard objects at a rate that increases by about 2.8 times compared to sea level on Earth. These high-energy particles, primarily protons and atomic nuclei, originate from distant parts of the universe and travel close to the speed of light. They interact with the upper atmosphere, creating showers of secondary particles and contributing to the ionization process. This constant bombardment is a reminder that even at the edge of space, Earth remains connected to the vast cosmic neighborhood. Yet, paradoxically, this intense radiation environment also serves as a shield for life on our planet's surface by reducing the number of harmful rays reaching lower altitudes. The thinning atmosphere above the Kármán line is not just a matter of fewer air molecules. It signals an ongoing transformation that will continue over billions of years. Over time, Earth's protective blanket will gradually dissipate into space, leaving behind only a wispy remnant of its former self. This process has already been in motion for eons, with the uppermost layers of our atmosphere slowly escaping into the void. By the end of this era, trillions of years from now, the planet may be left with only a thin veneer of gases, barely clinging to the surface. Yet even today, at an altitude of 100 kilometers, we can observe the first hints of this future state, a pressure so low that it is akin to the near vacuum found in interplanetary space. At this boundary, temperatures plummet to as cold as -85 degrees Celsius due to the lack of atmospheric insulation. The molecules of air are spread out so thinly that they no longer interact effectively, leading to a dramatic decrease in heat transfer. This extreme cold is not just a consequence of altitude, but also a result of the thinning atmosphere's inability to retain warmth. Interestingly, this temperature drop mirrors conditions found on distant moons like Europa, where icy surfaces reflect sunlight and radiate away more energy than they receive. Yet, unlike Europa, Earth's edge of space lacks any surface to hold onto heat, making it an even colder environment. As the atmosphere continues to thin over billions of years, its protective layer will gradually erode, leaving Earth increasingly vulnerable to cosmic radiation. This erosion is not a sudden event, but a slow process that mirrors the gradual cooling of stars at the end of their lives. By the time our Sun enters its red giant phase, in about 5 billion years, the atmosphere could be so thin as to barely exist above sea level. The pressure will drop to levels unimaginable today, akin to the vacuum found between planets. This future scenario would render Earth's surface inhospitable for complex life, yet it underscores the transient nature of our planet's current conditions. At this altitude, cosmic rays bombard objects with increasing intensity, their energy growing as they penetrate deeper into space. These high-energy particles originate from supernovae and black holes across the universe, traveling vast distances to reach Earth. At an altitude of approximately 100 kilometers above Earth's surface, a spacecraft encounters the ionosphere, a dynamic layer where radio waves are transformed and redirected back to our planet. This region, extending from about 80 to 600 kilometers, is crucial for long-distance communication. The air here is so thin that each molecule behaves almost independently, yet it contains enough free electrons to reflect certain frequencies of electromagnetic radiation. When radio waves enter the ionosphere, they encounter a layer rich in charged particles. This interaction can be likened to throwing a pebble into a pond. The ripples bounce back depending on the depth and density of the water. In this case, the ionized gases act as mirrors, reflecting radio waves back toward Earth's surface. The process is so precise that it allows for long-distance communication across continents. The phenomenon of radio wave reflection in the ionosphere is crucial for global navigation systems like GPS. Without this layer's ability to bounce signals back down, Satellites would struggle to maintain constant contact with ground stations. This thin region, extending from about 80 to 600 kilometers above Earth's surface, acts as a natural mirror for radio waves. It reflects them back toward the planet's surface, enabling long-distance communication and precise location tracking. The ionosphere's reflective properties are due to its charged particles, ions and electrons, that form when solar radiation strips atoms of their electrons. This process creates a layer rich in free-floating ions that can interact with radio waves, bending or reflecting them back toward Earth. At the edge of space, approximately 100 kilometers above sea level, this phenomenon becomes particularly pronounced. The ionosphere acts as a natural mirror for radio signals, bouncing them back to the ground, enabling long-distance communication. Imagine standing on a beach and throwing a pebble into a calm lake. When it hits the water's surface, ripples spread outwards. Similarly, when a radio wave strikes the ionosphere, it bounces back towards Earth. This layer of electrically charged particles acts as a natural mirror, reflecting signals that would otherwise be lost to space. The ionosphere's ability to reflect these waves is crucial for global communication systems, including AM radio broadcasts and satellite communications. At an altitude ranging from 80 to 600 kilometers above Earth's surface, the ionosphere forms due to solar radiation stripping electrons from atmospheric molecules. This process creates a layer rich in ions and free electrons, which can reflect certain frequencies of electromagnetic waves back toward the ground. Imagine this. While radio waves typically dissipate or are absorbed as they travel through the atmosphere, the ionosphere acts like a mirror, bouncing them back down to Earth. At an altitude of approximately 80 kilometers, where the air density is about 1/1,000,000th that at sea level, these reflected signals can be crucial for global communication. This layer of electrically charged particles allows radio waves to travel much farther than they could in denser atmospheres. Imagine a world without this natural mirror. Long-distance radio communications would be far more limited. At an altitude ranging from 80 to 600 kilometers above Earth, the ionosphere reflects these signals back towards the surface. This phenomenon is akin to bouncing a ball off a ceiling. Radio waves hit the charged particles in the upper atmosphere and return to us. But unlike a simple bounce, this reflection can span vast distances, allowing communication across continents. The density of air at the edge of space is so thin that it's equivalent to 1/1,000,000th of what we experience on Earth's surface. Yet, despite its near-vacuum state, the ionosphere plays a crucial role in our daily lives by bouncing radio waves back to Earth. This phenomenon allows for long-distance communication and even global navigation systems like GPS. Imagine you are standing at sea level, holding a flashlight emitting 500 nanometer light. The light travels in a straight line until it hits an object or fades into space. Now, consider the ionosphere as that object, except instead of reflecting visible light, it reflects radio waves back to Earth. This layer, extending from about 80 to 600 kilometers above us, acts like a mirror for certain frequencies of electromagnetic radiation. At this altitude, the ionosphere is a dynamic region where solar radiation strips electrons from atmospheric gases, creating charged particles that can reflect radio signals. These reflected waves are crucial for long-distance communication on Earth, allowing signals to travel around the globe without needing extensive infrastructure. This layer acts as a natural mirror, bouncing back radio waves that would otherwise dissipate into space. The phenomenon is so reliable, it has been used for decades in global navigation and military communications. Imagine standing at the edge of this ionosphere, where temperatures can plummet to -85 degrees Celsius. Here, cosmic rays bombard objects with increasing intensity, nearly 3 times more than they do at sea level. Yet, amidst these harsh conditions, radio waves find a surprising ally: the ionized particles that make up the upper atmosphere. These charged ions reflect radio signals back toward Earth, creating a natural mirror in the sky. Radio waves, typically absorbed or scattered by the denser layers of the atmosphere below, are deflected at this altitude by electrons and other free charges. This phenomenon allows for long-distance communication across continents and around the globe. The ionosphere acts as a dynamic layer, constantly shifting its height due to solar activity, which can cause it to rise or fall by several kilometers. At 80 kilometers above sea level, particles still dance in the vacuum, their fleeting bursts of light, a reminder of the cosmos' constant presence. As we near the end of this journey, let's take one last moment to savor the quiet beauty of it all. Thank you for joining us tonight on Cosmic Sedation. If you enjoyed this, feel free to subscribe and leave a like. Good night, and may your dreams be as vast as the universe itself.